Hello everyone, let's take a look at our next problem. When 1 plus 3x plus 5x squared plus 7x cubed and so on up to 99x to the 49 is divided by x minus 1, the remainder is 2,000, 2,500, 3,000, or 3,500. Interesting. Okay, so we have a fairly large polynomial. We want to divide by x minus 1. Another polynomial, and we want to figure out what the remainder is. So my first thought here is to do polynomial long division. That might be a very long process. My other thought is to, we're asked for the remainder, not the solution, of course. My other thought is to, it's kind of cheating, but to substitute a particular value of x and try and compute this whole thing, but that seems like, that doesn't seem, will that, if I substitute a particular value of x, will that be cheating? Will that give like an answer which is sort of valid for all values of x? I'm not sure. I'm gonna sort of pocket that idea. I'd rather not take approach which may or may not really give a proper answer. Yeah, so maybe long division of polynomials. Is there something else we could do maybe by writing out what it means? I think I'm going to start with polynomial long division. Given that there's a pattern in the original polynomial, I'm hoping that there will be a quick pattern that we can identify in the computations for the long division. And we'll just see what happens there. Now I have to try and remember exactly how to do polynomial long division. So what's happening here is, each additional coefficient that I have here, that's not a 0, this is supposed to be, a placeholder for something. Whatever goes here is going to be 99 plus 97 plus 95. And the new, which is, I suppose, 291, right? And then we just keep adding these coefficients together. And so what's going to happen at the end of this here is the final term which goes here, the term which goes here is going to be the sum of all the coefficients. I'll call that S. S will be equal to the sum of 2k plus 1, where k goes from 0 up to 49. And then, well, hold on. That would go, so if I redo this, the number that goes here above the 3, let's call this S. This will be the sum as k goes from 1 to 49. And then when I did, okay, so I would have S times x here. I'd take a difference. That would go away. And I'd end up with hold on, I'd have Sx minus S. When I take a difference, I get a 0 there. And here I get plus S plus 1. And then I mean, I won't be able to, this s plus 1 doesn't have a factor of x in it. It doesn't have a power of x. So when dividing that by x minus 1, that would give me a 0. And this s plus 1 would be the remainder. But that's actually the number that I had written down here originally. So s plus 1 is just the sum as k goes from 0 to 49 of 2k plus 1. This is the number I'm actually looking for. That's going to be the remainder of this division. So this is the sum of all the odd numbers from 1 to 99. So the sum of the odd numbers from 1 to 99. The trick I shouldn't say trick, the idea of how to compute this easily is we take the first number plus the last number and take their average and multiply by the number of terms we have. So there are 50 terms in this sum. The first one is a 1, the last one's a 99, so on average all the terms are whatever that is, and we multiply by 50, so what do we get here? 100 divided by 2 times 50, which is 50 times 50, which is 2,500, which is one of the options. That's option B. Yeah, and that's the answer. I went through some of this in trying to see the pattern that comes out in these coefficients. And well, first of all, remembering how polynomial long division works, that was I didn't remember the exact process, but once you start working it out, it kind of comes back to me. Seeing the pattern in the coefficients here and realizing that as I go down these entries here, we just keep adding up subsequent values of the coefficients, and then just trying to figure out exactly how this pattern extends to the last 2 or so steps in the division. That was kind of important, and realizing that this final the final thing we're looking for is just going to be the sum of all the coefficients. That was kind of the key in doing this. There's probably another way of seeing this by writing out. Maybe there's another way of seeing this by writing out exactly what it means to have a remainder after polynomial division, like in terms of the product of two polynomials is equal to the third plus a remainder, and trying to deduce exactly what the remainder was going to be there. But I'm fairly confident in my answer here of 2,500. But if I have more comments or if I find a mistake in what I've done, I'll put them in the description. Otherwise, thanks for watching.